As Nando mentioned, we're trying to build some hardware that can realize a certain kind of quantum algorithm. So as you might imagine, there's a lot of basic physics problems that need to be overcome. But interestingly, this is probably not obvious kind of initially, there's a lot of algorithmic challenges that also need to be addressed. And I think this community is perfectly well positioned to help kind of address some of those challenges. And hopefully what I'll get across today is what those challenges are. And if I succeed in my wildest dreams, I'll have interested some of you in kind of helping out to bring these early kind of quantum annealing machines to life. Let me start with some good news. So the origins of quantum computing are perhaps 30 years in the past now. But interest in the field really got kick-started in 1994 with the discovery by Peter Shor of an algorithm for factoring integers in polynomial time by exploiting quantum resources. So these are not kind of at all the typical algorithms you're sort of thinking about. These are algorithms that sort of piggyback directly on top of quantum mechanics to exploit some of the neat things you can do there to build faster solvers. As you might imagine, this result was unexpected and consequently generated a lot of interest. Shortly on the heels of Shor's algorithm came another algorithm that's kind of going to be more relevant to our discussion here. This is an algorithm that's come to be known as Grover search, basically named after its discoverer, Love Grover. So Grover's problem is the following. So imagine that I give you a list of all 2 to the n linked n bit strings. And I pick one of them out at random and mark it as being significant. And then I challenge you with the task of identify that needle in a haystack, find that significant bit string. It's classically there's nothing to go on because nothing is marked but the single bit string you're looking for. So making a wrong guess provides no information whatsoever. So classically the complexity of this is going to be ordered 2 to the n because you're going to have to look through all the bit strings. The remarkable thing is if you use quantum mechanics, you can actually solve this problem not in time 2 to the n, but square root of 2 to the n. Can everybody hear me? So this algorithm, unlike Shor's algorithm, it takes something exponential into polynomial. This is just kind of a square root speed up. So its problems still remain exponential, but you're gaining a big factor here. You're basically having the exponent in your complexity. So that's the good news. The bad news is that to realize these algorithms that exploit quantum mechanics, there's a lot of basic physics challenges. On the one hand, you need systems that you can program, so you need to be able to get in and dial all the knobs. But once you've done that, you basically don't want to touch them. They can't sort of interact with the real world because they're going to sort of break up all these delicate quantum correlations that the algorithm builds up as it progresses. So it's been a real challenge building machines that can run some of these algorithms. And so, for example, here we are, almost 20 years after Shor's initial discovery of his factoring algorithm. The largest kind of experimental realization of this algorithm has used a handful of qubits, and the largest number that's currently been factored is 21. So clearly, something needs to be done to kind of make better progress. So there was an interesting development about 10 years ago now that was a more physically grounded model for quantum computation that kind of provided the sort of the programmable control, but sort of buffering from kind of random noise sources that you need in these algorithms. And that's something called adiabatic quantum computation. And I want to talk today about a specialization of adiabatic quantum computation called quantum annealing. And it's this algorithm we're trying to realize in hardware. And this might all seem quite exotic to you, but it's actually, I think, given the background of this community, it should actually be reasonably accessible. If you know anything about simulated annealing, you're going to see an awful lot of parallels here, and a lot of mathematics is actually very similar. So I thought, though, before I kind of dive into some of the details, I'd give you kind of the nutshell, the take-home message that will sort of keep you on track through this thing. So in a nutshell, what we at D-Wave are trying to do is build a piece of hardware that will programmatically allow you to define energy functions. In our case, they'll be Ising energy functions. And then that hardware is going to exploit quantum mechanical evolution to rapidly, and the quantum mechanics helps you do this rapidly, to rapidly equilibrate to some distribution. Roughly speaking, think about it for now as a Boltzmann distribution with the programmed energy function. So the goal here is that you'll be able to now, use that energy function at low temperatures to, sample low energy configurations, or to do, use it as some kind of IID sampler. And the hope here is that this is going to be, you're basically piggybacking as fast as possible right on top of physics, so that this can all be done hopefully much faster than you could do in software. So the reason I was happy for the invitation to come here is I think this connects with your community in two ways. So the first thing, as a company, one thing we're interested in is actually people developing useful applications that can run on this hardware. So machine learning, we looked around, there's an awful lot of optimization goes on in machine learning. We know about Markov random fields, so it seems like a great marriage. So that one thing I want to talk about is, what are sort of the good applications for a device that does this kind of Boltzmann-like sampling in machine learning? And then secondly, as we'll see as I sort of dig into this, the hardware that we're building has a number of quirks. It has a number of limitations just kind of forced upon you by basic physics. And we have to find algorithmic ways of kind of circumventing these quirks. And I think this community is well positioned to help us kind of address those challenges. So I'm going to mention that towards the end as well. So what would I like to cover? Probably a lot of you do have physics backgrounds, but for those of you who don't, fear not. I'll give you enough kind of quantum mechanics background that you'll be able to understand quantum annealing. Then I'll talk about, because I think this is really interesting, how that algorithm, that theoretical algorithm, is implemented in a real hardware device. And I'll culminate that sort of discussion with some benchmarking results. How well does this actually work in practice? And then I'll turn to these two machine learning connections. One, how can quantum annealing potentially be used in new classes of machine learning algorithms? And then secondly, how can you guys help with kind of solving some of the problems of bringing quantum annealing to fruition? So let's start with quantum mechanics, as you might read about it in kind of a first-year textbook. A quantum system is essentially described by a vector, typically a very long vector, living in some Hilbert space. And things you might do to that physical system, out in the real world, like take measurements and so forth, are represented by matrices or operators acting on that state description, which is this vector in this Hilbert space. The interesting thing about quantum mechanics is that these operators, or these measurements that you can take on the system, are generally not commutative. And this is kind of where a lot of the interesting stuff comes from. So for example, if you had some quantum system and you meant to measure, say, the position of a given particle and then its momentum or its velocity, you would leave the system in a different state, whereas if you'd done those two measurements in the opposite order. So it's this non-commutativity that kind of makes things a lot more interesting. So given that, let's talk about kind of the simplest possible quantum system you could imagine, and that's the qubit. So this is the quantum analog of a bit. So the quantum mechanical description of a bit, or of a qubit, is this description is going to live in this little small two-dimensional Hilbert space. So in this case, the classical states, 0 or 1, are represented by two orthogonal vectors. So think about these two classical results, these two classical descriptions, as spanning a space. Now the interesting thing about quantum mechanics is you can actually have quantum states that live as linear combinations of those two classical basis states. And to get sensible results, all these vectors have to be normalized. So think about it initially here is that you've got these two, this funny notation of 0 and 1 is kind of physics notation for just vectors, but those are called kets. But just think of them as vectors, kind of indicating the 0 and 1 directions. So quantum states live on this circle then, where a normalized state is something on this circle, some linear combination of those two things. In fact, it's a little bit more complicated than that, because these amplitudes, these linear combination, these weights can be complex valued, but that's really not of any consequence for what I'm going to say. So given that quantum systems are now these linear combinations of these classical basis states, what's the meaning of those amplitudes? Well, the meaning of the amplitudes alpha naught and alpha 1 here is that if you had a qubit in this state and you were going to take a measurement on it, what you would see in your classical detector that measured the bits is you'd measure 0 with probability alpha naught squared, and you'd measure 1 with probability alpha 1 squared. So in some sense, this qubit is living in a combination of both states at once, and it's only when you go to measure it that you'll actually pick out a distinct value. So the extension to many qubits is kind of the natural one from what I just said. So in this case, if you have n qubits, there's now 2 to the n possible classical basis states, all the way from the basis vector 0, 0, 0, all the way up to 1, 1, 1, 1, 1. But just as before, the quantum state is going to be some linear combination of these 2 to the n basis vectors. So this qubit state is a vector in this 2n-dimensional Hilbert space. And just as before, the amplitude or the weight associated with any one of these classical basis states is the probability, if you were to take a measurement, that you would measure that joint configuration of bits. Okay? Now, as I mentioned, the second aspect of quantum mechanics is that there's operators. There's things you can measure about systems. And one of the most important operators is something called the Hamiltonian. Think about that as kind of the operator that measures the energy of the system. The Hamiltonian, so again, being an operator on this basis, is a big 2 to the n by 2 to the n matrix. It's a very important operator because it's this operator that governs how the physical system is going to evolve over time. So there's a differential equation that relates how the action of h, or this energy function on a quantum state, governs its time evolution. The details are not really important. What I want to get across here is that if you have a quantum system in conjunction with some sort of cold environment where it can lose energy to it, that the quantum evolution can actually act to, this Schrodinger's equation will act so that what the quantum system will do is you have this big matrix giving basically the energy of the system. The quantum dynamics will, what it'll do is it'll drive the system to the eigenvector of that big matrix corresponding to the lowest eigenvalue, or the lowest energy. So crudely, if you want to think about it, think about the quantum mechanics as kind of doing a diagonalization, finding the ground state, finding the lowest eigenvector of this big matrix. So given that's what kind of quantum physics wants to do by its nature, we want to harness that to be able to do optimization, to minimize classical energy functions for fun and profit. So how are we going to do that? So let's say we had some classical optimization problem P that we want to minimize. And this is an optimization problem defined over bit strings. So the first thing I'm going to do is, for each possible enumeration of the bits, for all 2 to the n configurations, I'm going to imagine a Hamiltonian where those appear on the diagonal. So that if I now go to diagonalize this big matrix, all that's going to do is pick out, the eigenvalue will be the lowest energy, and the corresponding eigenvector would be the bit string that actually gave you that energy. So, the nice classical world of optimization that we're used to thinking about is just quantum mechanics that lives on the diagonal of the Hamiltonian. And in the hardware that we're developing, at D-Wave, the kinds of energies that you can put along this diagonal are Ising models. They're actually a restricted kind of Ising models. But they are Ising models. So all these parameters, these h's and j's, for the linear and coupling terms that you can describe between bits, are user definable. There is a significant constraint, though, is that for some of the qubits, because as you'll see, these actually have physical analogs in a piece of hardware, you can't program interactions between all pairs of qubits. Only certain of them can you have programmable interactions. And the remaining qubits are of necessity, the interaction has to be 0. So you can think about it. Think about this as there's some factor graph underlying this Ising model that's, in our case, is actually quite sparse. Now, the fun begins when you start to add quantum mechanics to this picture. So what happens? So now, programmatically, because we have a quantum system, just as we could program in the h's and j's, here we could program in some other terms that have no classical analog, but they're energy contributions, that actually govern the evolution. So in this case, you can see what I've highlighted in blue. These are other programmable elements you could set into this matrix. And they exist between pairs of states that differ by a single bit. So what this means is that the quantum system can actually have bit flip terms, and actually can gain energy by flipping bits. So the action of h, when you apply it to some quantum description of some state, will actually go to flip some of those bits, and there can be an energy loss or gain based on those bit flips. Otherwise, everything is the same. The physics is still going to drive you towards finding the eigenvector corresponding to the lowest eigenvalue of this matrix. Now that gets interesting because this is no longer diagonal. When you find the eigenvector corresponding to the lowest eigenvalue here, that eigenvector is going to be a linear combination of some of the classical basis states. So we're not back in the classical where you pick out a definite bit string here. Here you're going to be in what's called in the physics jargon a superposition of classical basis states. And there's going to be an amplitude on all those classical states. And so if you go to actually measure operations in that eigenvector, in that physical description, you're going to obtain a stochastic description, obtaining certain values of the bits, depending on what those amplitudes are. So it turns out that this superposition effect that you get from minimizing these matrices with these quantum interactions is going to be very important. And that's what we're going to exploit to do better optimization. So what I'm showing here is an interesting phenomenon that follows from that superposition principle. An interesting thing that you can actually do that we're going to harness as a resource. On the left-hand side here in blue, I've drawn some potential function. And I'd like to minimize this function. So imagine that you're trapped in the left-hand well and you'd like to actually find the global minimum over on the right-hand well. We're probably all familiar with the idea of simulated annealing, where if I kick it with some thermal energy, I can climb those energy barriers in the hopes of finding my way over to that better basin, over to the right. Quantum annealing is very similar in spirit. We're going to use some other kind of fluctuation, in this case not a thermal fluctuation, but some other process that allows movement between local minima. In quantum annealing, what's interesting though is that this process will work even at zero temperature. So what I'm going to take is, now imagine that this potential function that I've drawn over here, there's some big matrix, and it's this potential function that's appearing along the diagonal of that matrix. So in that graph over on the top right, I don't know if you can see it, but there's a little dashed red line, which is this potential from the left. And then the blue line, so not the jiggly jags over here, but the graph on top of that. That blue line is if in the quantum system that minimizes this energy, that gives the probability that if you actually measure that quantum system and ask, where would I find the particle? That's what that probability is. So in this case, you can see that it's peaked in those two wells, the one on the left and the one on the right. Interestingly, in this case, there's actually more probability of finding it in the well on the right, or on the left, rather than the one on the right. And the reason for that is that there's another contribution to the energy beyond just what the potential energy is, just this blue curve on the left, but a kinetic energy. So the particle actually, quantum mechanically, likes to be able to kind of spread its wings and kind of move out, to kind of occupy as much space as it possibly can. And that's why you can see that well on the left actually is a bit wider, its basin is a bit broader, so the quantum mechanics can actually prefer that situation because of that effect. But what's interesting about that is when you do the quantum mechanics, it maximizes the probability in the two wells. But if you look closely, you'll see that the probability between those two wells, so the probability of measuring the particle at states in between those two wells, where the energy can actually be significantly high, that probability is non-zero. And what that means is that you can actually, because there's some chance of seeing the particle there, you can harness that through a process called quantum annealing. So quantum annealing is kind of illustrated in this nice figure down on the left that I pulled out of this paper down here. So what I've done here is I've flipped it so the y-axis now is my potential, and I've imagined, and time is running off to the right. So this is a simulation of what a quantum particle might be doing in those wells. So the particle will start off in some well, but then because there's non-zero probability of finding it, say, at higher energies between the wells, it'll slosh around in a well, and then all of a sudden make abrupt transitions between wells. Tunneling, it's called tunneling, because unlike simulated annealing, it doesn't have to climb the energy barriers. It can actually sort of tunnel right through these kind of energy barriers into the next local minimum. And this all happens relatively quickly because those are actually high energy states. So this is a really interesting phenomenon. This is not, the physics is really doing this. So it's an interesting way of escaping local minima, poor local minima, in the hopes of finding better local minima. So the goal here is going to be to harness this propensity of nature to do these things for a more effective optimization, classically, so that you guys can go and program an objective function, piggyback on top of physics, and exploit this process. So that's quantum tunneling as kind of this sort of escape mechanism from local basins of attraction. How are we going to harness that in an algorithm? So here we're going to take our cue from simulated annealing and kind of play the same kind of game, but now rely on these quantum fluctuations rather than thermal fluctuations. So this is one realization of how that works in practice. Here's one thing you can do. So I'm going to make a time-dependent energy function, or a time-dependent Hamiltonian, a big time-dependent matrix. And on the diagonal, I'm going to encode my problem that I want to solve. Remember, that's just all the energies kind of stored along the diagonal. And then on the off diagonal are all these bit flip operations that actually act to kind of sort of delocalize the quantum state, and explore multiple possibilities at once. Just as I simulate annealing, I'll start at really high temperature. I'm going to start where most of the contribution of the Hamiltonian comes from these off diagonal contributions. So I'm going to start in a purely quantum mechanical state with zero contribution of HP. And then what I'm going to do is turn down the quantum stuff, basically turn off my off diagonal elements and turn up my problem elements, which are on the diagonal. Now, what's interesting about this is that when I'm in my quantum state to begin with, the lowest energy state of this off diagonal stuff assigns basically equal probability to all bit strings. So if you were to actually put the system in that initial state and then measure it, all bit strings would be equally likely. And then I'm going to slowly evolve that initial probability distribution over the space into one where at the end of the computation, I hope that all my probability mass, if I go to measure this thing, is concentrated on the global minimizer of my Hamiltonian, of my energy function that I'm trying to minimize. So that's the basic intuition for the kind of algorithm we'd like to build. So here's another kind of view on that. This is a really important picture because this basically determines how fast algorithms like this can be. So on the left-hand side, I'm starting out where my Hamiltonian, my initial matrix, is all quantum and none of my classical problem is mixed in yet. Now that's a big matrix. It has a bunch of eigenvalues, and those are kind of marching up the y-axis. It's easy in this system for the physics to find the lowest energy state there. That's the state that assigns equal probability to all classical bit strings. But as I march my time forward, I'm going to evolve my Hamiltonian to start decreasing the weight of the quantum terms and increasing the weight of the classical optimization problem that I'm trying to minimize. But at any moment in time, I could imagine doing the same process and diagonalizing this matrix to find all the eigenvalues. So that's what all these kind of sort of notional lines are. That's kind of how the spectrum of this matrix evolves as I change time. The idea here is that I can easily set things up so that I start in this red dot at the minimum of the quantum Hamiltonian, and then evolve step by step, change my Hamiltonian, change the time, hopefully always keep staying in the ground state so that at the end of the computation, where I'm left in purely the classical problem that I wish to minimize, the state that I'll be in then is the minimizer for my classical problem. So how can this go wrong? Or said another way, what's going to limit how fast you can drive this algorithm? So what can happen, fundamentally the process is relying on knowing the answer, or getting a physical system to know the answer at time t, to kind of bootstrap itself up to kind of figuring the answer out at time t plus dt. So evolve from the ground state at time t into the ground state at time t plus dt. So where this can mess up is in regions where some of these excited states, some of these states that are not the ground state, become very close in energy to what was the ground state. And in fact, there may be transitions where what was the ground state at time t plus dt, a little bit later actually becomes, say, the first excited state, and what was an excited state now becomes the ground state. So in regions where these eigenvalue spectra come close together is where you have to actually make sure that your ground state can actually track and make sure that it actually stays in the lowest energy state as it goes along. If you drive too quickly through those transitions, you'll find your way up into some of these excited states, and then at the end of the computation, you won't actually be in the ground state of the classical problem you want to solve. So what's going to drive how fast you can, what's going to determine how fast you can drive this algorithm are these gaps. How close do these spectra come to each other as a function of the annealing time? So if you have a really hard optimization problem, this is where the difficulty is manifest. If you have a really hard problem, typically what's going to happen is that the gaps somewhere along this line here, somewhere along this annealing time, will get quite small. And in fact, they can get exponentially small, so that the complexity is as expected. Even quantum annealing is not going to solve, it's not going to take exponential things to polynomial in general. So that's where it gets manifested. That you may have to move sort of exponentially slowly through these regions, to kind of, because the gap is closing exponentially fast. But this picture, it's this picture that actually gives you the square root speed up that I talked about for Grover's algorithm. So remember in Grover, in this search problem, instead of taking time 2 to the n, it took square root of 2 to the n. And the reason is because if you look at how fast this gap closes, you know, when you sort of work it all out backwards, it turns out that you can drive this calculation, drive this algorithm, so that it'll only take square root of 2 to the n rather 2 to the n. And these, Grover's search is kind of the worst case. The energy landscape there that you're minimizing is like this golf course potential. It's flat everywhere, except at one marked configuration where the potential drops. So it's kind of the worst case, the worst possible case. So this quantum annealing, I know that I think even in this community, it's been used as a heuristic algorithm, this quantum tunneling process, to solve classical optimization problems. So the idea there is to simulate the quantum mechanics in software in the hopes of building a good heuristic minimizer. That's not at all what I'm going to be talking about here. Here we're actually using physics itself to do this minimization for us. So there's nothing simulated in the quantum mechanics. We're building a real hardware device which does this minimization for us. So in some sense, what we're trying to do at D-Wave is to compute things like this as fast as physics can possibly allow us. So given that we're going to realize this in a hardware device, we need qubits. So what are the qubits that are leveraged in the device that we're building? So our chip is actually, the basic qubit is a little loop of superconducting wire that's cooled to almost absolute zero, so that it actually is exhibiting macroscopic quantum effects. And our 2 qubit states, our two sort of preferential zeros and ones, are going to be, what is the direction of the current flow in that loop? Is it going to be flowing clockwise or counterclockwise? So for those of you that remember your right-hand rule from physics, you can induce currents by magnetic fields. So if I put a little bit of a magnetic field up through that loop, that's going to induce a bias to have this current circulate, in this case counterclockwise. And likewise, if the field is down, then it'll rotate the other way. So by threading little bits of magnetic field or magnetic flux through these loops, I can induce bias terms, and these are going to act as the H's, or the linear terms in my Ising model. Likewise, it turns out if you get into the detailed physics here, if I introduce a little secondary loop over here on the left and thread some magnetic flux through that, these act as the bit flip terms. And so with those sort of tunably setting the amount of magnetic field I put through those loops, I can control these off-diagonal elements delta in my Hamiltonian. So with a basic device like this, I can get programmatic control over certain aspects of my Hamiltonian. Of course, the thing that's missing so far is in the Ising model is the J's. How do I couple qubits? So it turns out that in these qubits, it's not important that these are actually little circular loops of current. They can be pulled and stretched like elastic bands, and the picture is exactly the same. So what I'm going to do is actually on the device, I'm going to stretch out my qubits so they're long and skinny. But still by threading flux anywhere through that loop, I can get these kind of biasing effects. But the advantage of having long, skinny qubits now is that they can overlap with each other. So this is a picture of our unit cell. So we built a unit cell here of 8 qubits, 4 vertical qubits and 4 horizontal qubits. And where they intersect with each other in these blue dotted regions, there's additional structures that allow those 2 qubits that intersect at that point to interact with each other. And these additional blue structures are also programmable, and they're going to act as the J's in your Ising model that you can programmatically set. So now the advantage of kind of building a unit cell, this was kind of purely an engineering concern. You want some basic repeating structure that you can tile out over a plane to get some computational fabric to scale things up. So here's a different view on that unit cell. So in the middle here, I've highlighted one of those unit cells in a different way. So each dot now is a qubit, one of these loops. And here I've just drawn the kind of programmable interactions that you might have between those qubits. So this is kind of a factor graph picture of the kinds of models we can realize in hardware. So the qubits on the left-hand side of this unit cell would be the vertical guys. The qubits on the right-hand side of this unit cell, of this bipartite graph, would be the horizontal guys. The way we connect up unit cells is that the vertical guys are connected to vertical qubits, to neighbors in the north and south, and the horizontal guys are connected to neighbors to the east and west. And our goal is to basically tile the plane, build a big lattice of these things so that you can build models of this structure. So up until very recently, we're just now starting to get chips that are of size 8 by 8. So an 8 by 8 array of these basic unit cells, each unit cell consisting of 8 qubits. So I'm hoping to get my hands on one of these chips in a couple of weeks in September that'll have 512 qubits with a bunch of programmable H and J values. And the way that you operate this thing to kind of get it to compute for you is that there's an initial phase where you program in your H's and J's. So basically the machine language of this chip is you tell it what are your H's and J's. And in our case, we have MATLAB and Python interfaces that you just give it a little matrix saying, these are my H's, these are my J's, quantum mechanics, go do your stuff. So that initial description of H's and J's gets programmed onto the chip through realization of these magnetic fields. And then repeatedly, you go through these annealing cycles, this quantum annealing process, that hopefully samples low energy states, and then read out the state of your qubits. Remember that I said it's really important. The quantum mechanics is inherently stochastic. You see things probabilistically because these amplitudes are all probabilistic. So it's very important that you do this many, many times because it's not a deterministic machine. So that the way, the typical operation of this machine is you program it once. The hardware guys who have developed the hardware have made it so you only have to program it once, and then you can iterate many, many cycles of annealing and readout. So you can draw many, many samples. To give you a sense of timing, in the chip that we're going to have online in September, you can do the programming and draw 1,000 samples from the models in about 100 milliseconds. So to give you a sense of how complicated are the icing problems that this chip can solve, the tree width of this graph that I showed you here, this factor graph here, is 33. So it's kind of not inconceivable that you could solve, but it's large enough that you need a lot of memory. And of course, as we scale the chip up, the tree width is rapidly going to become large enough that you can't do anything practical with it. So that's the basic processor that we're going to use. To get the thing all to work, there's a lot of surrounding infrastructure that's needed. The chip, this processor, this kind of computational fabric of lattice qubits is put on a motherboard. There are connections to wires that go to computers back at room temperature that allow you to send down the H's and J's. It's really important that the environment that the chip lives in is as quiet as possible. There's as few kind of stochastic, uncontrolled stochastic effects as possible. So there's a lot of filtering from the signals to kind of limit electrical noise that gets sent down to the chip. And then the whole thing is dipped in this fridge to cool it to 20 millikelvin. And because all the signals, all the programming signals are magnetic, it's put in a magnetic shielding environment so that there's virtually no kind of stray magnetic fields here. So there's a lot of plumbing around it to kind of make the thing work. And that introduces a lot of complexity that I didn't mention originally when I was describing quantum annealing. The fact is that this chip is a long way from that idealized description that I described. The effects that you have to worry about are the fact that the chip, while it's very cold, is not at absolute zero. So it's living at some finite temperature. And secondly, it's interacting with an environment in a way that's not knowable by you, which can potentially muck things up badly. Now, what's interesting is if you're going to try to kind of accommodate for these effects, I think what's interesting for this community is both of those effects have graphical model counterparts that I think will be familiar to all of you. So the finite temperature stuff is kind of you're all used to dealing with probabilistic models, and all the classical statistical physics that you know and love has counterparts in this quantum world. So a lot of the things you might, notions of Markov random field, conditional independence, all of those have kind of quantum generalizations. What's interesting though is that you're not dealing with probability densities anymore, but something called density matrices. They're like kind of Boltzmann probability models, except instead of like e to the minus beta some energy, it's e to the minus beta some Hamiltonian, where the Hamiltonian is itself a matrix. So the fundamental object of interest is this matrix, it's this exponential of the Hamiltonian. But think about it as kind of like in a graphical model, except now you kind of generalize things from probabilities to these density matrices. But a lot of the tools you're familiar with, like belief propagation, have quantum counterparts. So there is a quantum version of belief propagation. But it's a lot more complicated in the quantum world because of this non-commutivity. So that these, if you like to think about these clique potentials that you might define in a graphical model, now become non-commuting operators. And that adds a lot of complexity to the underlying algorithms. But in principle, a lot of the machinery that you're familiar with has straightforward generalizations into this world. So in principle, you can learn a lot about the finite temperature behavior. Likewise with the environment, you can think about the environment. So you have your model describing your system. That's what you'd really like to be able to deal with. The reality is that not only do you have that model of your system, but there's some coupling between your system and the outside world. So there's some unknown coupling between your system and the environment, and you want to integrate out the environment to see what the effect is left on your system. So essentially this is a hidden variable problem. So that's why I was mentioning earlier that even if your system is equilibrated, so the joint system plus environment has equilibrated to a Boltzmann distribution, by the time I integrate out all my hidden variables, all my classical, all my environment, what's left on the original system may not be Boltzmann at all anymore. So that just goes to say that a lot of the tools that you have are kind of ways to kind of tackle how does real kind of idealized quantum annealing at zero temperature generalize in this more realistic case. So what is the prognosis then? Do we actually think that we can build scalable quantum annealing machines? The finite temperature effects appear to be relatively benign, as long as you can keep yourself to low enough temperatures. And in some cases, it actually helps matters because it fosters more exploration. You can actually take that, you can actually gain some benefits from that. More problematic are these environmental couplings. And so that's why we've gone to great pains to kind of limit the amount of electrical noise that's coming down to the chip and shield it from stray magnetic fields. So in fact, we've done sort of a good enough job there that most of the noise that's relevant now actually comes from the chip itself. When you go to fabricate one of these devices, there are defects, and not all the qubits are created identically, and those sources of noise are actually the dominant problem in chips like this and scaling it up. So some of these effects will definitely become important as we scale things up. So far, we haven't found any reasons to kind of insurmountable hurdles. There may be some of these environmental coupling effects that we'll see starting to damage the performance when we start to get up to these 500 variable problems. But what's nice about sort of the prognosis for the future is there's a lot we can do to kind of drive the noise level of our chip down through better fabrication. And the modeling that we've done says that we can drive the noise down, say, by a factor of 10, the inherent noise in the chip. We can actually scale up the size of these systems we can build by a factor of 10. So that's kind of the theoretical and the practical kind of view on quantum annealing. How does it actually do in practice? So as you might imagine, this was kind of one of the first things that we tried. What we do is we want to take a bunch of icing problems, send them to the chip, and see how well physics can do this minimization for us using this process. So what we did is take that factor graph that I've shown you, and for all those programmable edges that were on there, assign particular h and j values. The early versions of the chip on this 4x4 lattice are all small enough that we can solve those models exactly. We can use belief propagation or mixed integer programming or whatever to find actually the globally minimal states of those icing models. So then we can program those values in and ask, how long does it take the hardware to solve these problems as a function of the size of the problem? Okay? So these were some of this graph on the left is some of the earliest experimental data that we took. So on the y-axis is how long in microseconds did it take quantum annealing to find these ground states as a function of the size of the problem for randomly generated instances. And you can see the really encouraging thing that we saw for these problems was that at least at these scales and for these problems, things seem to be scaling linearly. The graph on the right is kind of the next generation of these experiments. The red dots you can see there are these blue dots that appeared on this, just repeated what was on this left-hand curve. The light blue dots are an extension. So we've tried 8x8 versions of this chip. We've got some preliminary results there. And as you extend this scaling on a completely new chip now out to larger numbers of variables, you see roughly the same behavior. The complexity is definitely going up, and it looks like it's going up faster than linearly as was in this case. But it's still a very moderate growth. By comparison, this green curve is a heuristic algorithm that's actually good at these, it's iterated taboo search. It's actually quite good at solving these kinds of 0-1 pseudo-Boolean optimization problems. But as expected, that heuristic, if you drive it hard enough to actually ask for ground states, globally minimal states, the complexity of that is going up exponentially to get this straight line. The top purple curve is, if you actually include the programming time into this whole process, so these things are just recording the annealing time. It turns out that for the hardware we're building right now, the tallest pole in the tent is actually the time it takes to program the chip. Everything else happens on the order of microseconds. So if you include in the programming time, you get this purple result here. So I'm really excited as kind of an algorithm guy that gets to play with this, to kind of look at how this performance is going to go in the region, kind of as we push this thing further, where we actually have access to a device that can give results that can't be obtained classically. I'm going to skip a bit of stuff here. There's a version of this chip at USC. A lot of the same stuff about simulated annealing, where if you anneal more slowly, if you cool it more slowly, you can get better results. Theoretically, that should happen here. And in some of the experiments that's been done at USC, the same thing happens. You anneal it more slowly, you get better results. So let me now sort of close with a bit of a speculation, maybe a hopeful speculation on my part, but this is something I really believe will come to fruition. Within the next 5 years or so, there will be hardware devices, probably a lot like this, that can allow you to define certain kinds of optimization problems, over problems of say 5,000 to 10,000 variables. And you'll be able to use kind of these algorithms to piggyback on this quantum annealing process to sample low energy configurations. It's not known exactly now how fast you'll be able to do this, but it's likely that it's going to be a lot faster than you ever could do these classically, particularly as you get to larger problems. And fundamentally, these machines will be stochastic. You'll be sampling from some distribution that's going to bias you towards low energy configurations. So let's take that as a given. As I've kind of alluded to, these machines are going to have some quirks. They're going to have some limitations. The most important of which, kind of, I think you've already met, is that they're going to be Ising models. But also, they're probably going to be sparse Ising models. It's hard to build hardware that has a lot of connectivity. Because all those edges, all those sort of order n squared edges, have actual physical counterparts. So it gets to be problematic to build a lot of edges. So what we'd like to be able to do is, given that this machine is going to be really good at solving certain classes of problems, how do we bootstrap that capability to be able to solve more arbitrary problems, the types that you guys in other industries would be interested in? Here's where we turn to the need for, the expertise that resides in this community to help us take this sort of basic one-trick pony that does what it does and leverage it in more interesting situations. I think in the interest of time, I'll probably skip over most of this. So one thing that we didn't, perhaps we were a little naive when we kind of entered in this game, but we looked around, having built kind of this hardware device, we need a source of optimization problems, in particular Ising optimization problems that we can, hopefully turn this quantum mechanics into real dollars. So it seemed, as an outsider's view, it seemed like there's an awful lot of optimization that goes on inside machine learning. So why not look there as a source of problems? Well, it was kind of a bit of a slap in the face. It'll be kind of all secondhand to you guys, but though there's an awful lot of optimization goes on in machine learning, very little of it is combinatorial, at least as far as I know. So I would welcome kind of feedback from anyone to kind of suggest places where combinatorial optimization is used within machine learning. So there wasn't as much low-hanging fruit in machine learning as we were initially hoping. The places where we did find stuff was in structured classification, so where you're trying to learn mappings from some inputs into a set of bit strings. And they're the kinds of things that kind of, we found to our delight that kind of map pretty well onto this scenario, is that in things like conditional random fields and structured support vector machines, there the basic idea is you build x-dependent Ising models and then minimize them to find, some pattern of bits that you're going to associate with that x. And whether you're doing that, whatever your objective function is, whether it's a CRF or some margin-based loss, you guys have invented lots of nice algorithms to kind of determine the dependence of h and j on x. And it's just left to us in the hardware to actually minimize these models that give you the subgradients or whatever you need for your learning algorithms. The other place that we'd seen some potential applications of being able to solve combinatorial problems was in hopefully doing some kind of L0 regularization of models that you might have. So here the idea, this originally originated with a collaborator at Google, Hartmut Nevin, and one of his students, Basil Denchev. The idea was, let's build a binary classifier, as usual, by taking some linear combination of features. But instead of taking some arbitrary, continuously valued linear combination of features, take a 0-1 linear combination of features. So basically, start with a large set of features and take, include some and throw some out. So if you want to regularize this with an L0 penalty, because these things are already binary, because they're already 0 or 1, the L0 penalty just counts up the number of non-zero coefficients. So this just basically acts as a linear term in your Ising model. So as long as your loss function is quadratic, at the end of the day you get out an Ising model that you can use to build an L0 regularized classifier. And we've recently been looking at how would you extend that into doing matrix factorization and stuff with these L0 penalties, where you solve the discrete part of the problem in hardware. So that's kind of some of our first forays. I'm really interested in talking to people if there's other places that you think you might be even better suited to being able to solve combinatorial problems. But let me turn to the last topic, which is basically I'm hoping today that I can intrigue you enough that you'll kind of buy into this message and try to help us extend the functionality of this to broader classes of problems. So fundamentally, the issue we have in building devices like this is that we have a fixed factor graph where we can solve problems on that factor graph perhaps faster than you can do with any piece of software. But if you meet a problem that doesn't happen to match your factor graph, it has higher order interactions, or if it's a simulation and there doesn't even have a mathematical description in terms of a factor graph, you'd still like to be able to leverage this kind of optimization capability to solve that more general problem. So that's question one. Are there ways, the techniques that have been developed here can help us do that? Question two is something that we haven't really thought about at all at D-Wave, nor has the quantum computing community. And that's, that fundamentally this hardware is stochastic. It allows you to define highly multimodal distributions over bit strings and sample IID from those distributions, sampling, all kinds of different peaks. The gotcha, at least as far as I understand it, you guys may have better techniques, is that the distribution that you're sampling from, you cannot know. If you could know it, then that would mean that you could actually solve the quantum mechanics, which you cannot do. So are there ways of leveraging this kind of Monte Carlo aspect to build Monte Carlo algorithms? So I think I just have a little bit of time. Let me just elaborate on that a little bit, those two issues, and convince you that, at least to us as outsiders, these seem like really genuinely hard problems that we don't really have good, acceptable solutions for yet. You probably all know that if you have some interaction that's higher order and you want to reduce it to a pairwise model, it's actually quite easy. It just costs the introduction of a few extra variables. But in a world that we live in now where qubits are a very scarce resource, you don't want to introducing an extra variable means introducing an extra qubit, and that's extremely costly when you go to such pains even to build a 500 qubit device. So you want to be as efficient as possible at reducing higher order models down to low order models. Secondly, even if you do have a low order model, let's say it's pairwise, it is an Ising model, the connectivity of your particular model may not match that underlying connectivity of the graph. There is again a way to solve this by introducing extra variables. So what I can do is I can take, in my original problem that I want to solve, map that original variable onto many qubits, and then ferromagnetically slave these qubits together so that in low energy states, all these slaved qubits will always assume the same value. So a problem variable becomes many qubits, and this is an example of how you could work. This was using the hardware to find some small Ramsey numbers, an experiment we did. But the light-colored qubits here all represent the same problem variable. But the fact that a problem variable gets translated into this sort of spaghetti mess of qubits down on the chip means that these sort of spaghetti pieces of qubits now can interact with more qubits than they would otherwise have been to. So you can actually mimic connectivity at the cost of qubits. Unfortunately, again, that's costing you qubits. But more than that, it's finding these embeddings so that you map from problem variables to qubits in a way that is efficient. That itself is an NP hard problem, and in a lot of cases, maybe more difficult than the original problem you went to solve. So while this method is effective at small scales, it's not scalable to large systems. So this is not a good way of actually addressing some of these factor graph challenges. Another issue, hardware is never big enough. That's particularly acute here because we got so few qubits. So problem decomposition becomes a huge issue for us. And a lot of the techniques that we've looked at, like Lagrangian relaxation, just don't work. And hopefully we're being naive and there's better techniques out there, but we still currently don't have good ways of doing problem decomposition either, or even I would say, honestly, good ideas. And as I mentioned, the whole Monte Carlo aspect, we have a lot of people on Wall Street that have asked us about this, but we really have no good response to them. We haven't even started exploring this issue. The optimization questions are daunting enough, let alone kind of getting into Monte Carlo issues where we have to deal with the whole low-lying energy spectrum. So I think my time's up now, so let me just kind of wrap up there. Hopefully I convinced you that there's a real new class of hardware coming online that you guys might be able to take advantage of in the next 5 years. So I'm hoping to kind of intrigue you to get in on the ground floor and think about algorithms. If you did have this as an arrow in your quiver, what would you do with it? But secondarily is, we could really use the help here in bringing this technology to fruition. As I mentioned, there's some really fundamental algorithmic challenges here, mainly dealing with this constrained factor graph. And I'm really interested in learning more, and there's a couple of representatives from D-Wave here. We really need help on how to address some of these algorithmic challenges. So I'm hoping that for any of you that have any kind of interest in this, that you can sort of jump into the game and start to provide some insight here. I realize these are hard problems, and for a lot of this community, they're probably not new, but hopefully this has given you an incentive that they're actually maybe an entirely novel way that you hadn't thought of, that some ramifications of some of the algorithms you develop could actually contribute to actual quantum annealing hardware. So with that, I'd like to close it. Just as I've said, anybody has anything they want to learn more, or they have ideas on literature that we could look at, work you've done or others, we need to hear about it because we're here to learn from this community about how we can address some of these algorithmic challenges. So I'd encourage, I'm here for the next couple of days, I'd encourage people to come talk to me or drop me a line. So I'm really grateful for the opportunity, Kevin and Nando, and with that I'll take some questions if there's any interest.